So I will present you Tanatloc, that is an interface of FreeFEM, but not only FreeFEM, there is actually GMSH. In the future, I think others finite element engine. Just for start, a brief presentation of your enterprise. So it's really small. Half PhD, half mechanical engineer on the other people. That doesn't care here. And the goal is to build heat pump to store energy for a long time. I don't know how it works. Don't ask me anything on this part, I don't know. And we need a lot of physics and multi-physics. So, for example, mechanics, so in mechanics, contact, mechanics, and coupling between a lot of physics. First, we have to, in 2017, when we were 2 people, we have to choose a framework to do a simulation, and all the commercial software don't do what we want. So we choose an open source software and customizable, and we choose FreeFEM because I use it during my PhD thesis. So now the problem is the mechanical engineer don't know what is the code, what to change, and all the time they change the code or is broken. So we need a graphical interface, only buttons, to allow the engineer to use your model. And we decide to build this software with a result visualization, post-processing tools, and stuff. So the global needs for a simple user only, really important, no code. They don't see anything in the code. Direct geometry integration from the CAD software, so the common format of files is step for 3D and BXF for 2D. And we can integrate more and more formats. This is not a complicated part. Automatic meshing with automatic refinement. This part is hard. Easy parameterization of the model, solver, all the things that are here. Easy binary condition selection. This is really hard in FreeFEM when you have a big 3D geometry with multiple phases to select only the one you want on a group of surface you want. On the easy one, the Tanatloc the terminal never, and post-processing tool. There is a few for now, but we can add it on demand. So the framework we choose is a web-based application for multiple reasons. React for people who know what this is. It's clearly not important. And there is a client and a server. This is common for web-based application. And that allows to deploy the application directly in a cloud or in a cluster. You can use it on your computer as a server, or you have directly a desktop application. This is Electron. This is a desktop application. And for expert user, they want to write custom models, custom code, custom FreeFEM code. Visualize additional data that are not directly coded in the available models on the parallel one. So we add some features a code editor directly in the application. There is some sort of, you can select a point on geometry, output data. There is a direct FreeFEM MPI support in all the scripts. We will build a Slurm interface to communicate with a computational cluster. And we equally do on request development. So this one is a pay feature because that take time. And we have a first collaboration with Denso and Professor Atsushi Suzuki. This first collaboration really helped us to develop for the first phase of development on bug feedbacks and a lot of stuff here. So how it works. This is almost the template. This is not, for example, here is the GMSH part when you build the mesh. So we have a sort of .go file of GMSH, but in fact, this is a template that is interpreted by JavaScript and compiled to a geo file. So I think for FreeFEM, this is more clear. There is no word of FreeFEM here, but this is a FreeFEM code. This one is a FreeFEM word. The rest is JavaScript that is compiled using this one. There is a model for the description of the problem. This is mainly to say in the interface, for example, my finite element space is this part is a P2, P1, for example. And for the post-processing, this is for you, this is in the type. This one are not complex. This is just argument, function of arguments. So this is the workflow of the code of the letter. This is not it's really complicated. But in the interface, you can select parameterize all the ones, so the geometry, the mesh, the material, the parameters of the simulation, the solver parameters, the boundary condition, the computational resource, for example, the file. After they automatically build the mesh, so you use the template, compile it, one GMSH, output the mesh, and the mesh is converted to a WebGL format to see it in the browser. After the FreeFEM template compile, run, that output result in data, and all the stuff is converted again to a format to see it in the browser. And after you can parameterize to post-processing, and again that run parallel for training input, and output a result as a visualizable things. So for example, I don't think a fish on the web, so I think I found a shark. So Houssam will present you more in detail after how it's work, but I just use a equation, parameterize it, generate the mesh. And this is so we don't see a lot the mesh. Yeah, there is the mesh, and there is the solution. I just put a boundary condition. This one is here. This is one, and this one is here. This is 0. This is just to see how it works. So the main target of the software is firstly the engineers to allow to access simulation in the easy way. And the second data writers is for the academics, so the student, teacher, researchers, with the custom model through the editor. So the feature of the software are already simple model integrated directly to either statistical analysis, so there is thermal problem, I think. You can easily set up your geometry, your parameters. You are direct from geometry to results. You can visualize your result of post-processing. You can export it to see it in PowerView if you want. There is data visualization. I think Houssam will show you that after. We have the editor. This is quite new, so this is bugs for now, but we improve it with time. And there is a quite collaborative tools, not on the desktop version, but on the cloud version. You can share with organization, with people. This is useful for enterprise. So some more information, we have a sort of GPL license. The eGPL is just for software work on the web. This is GPL. We are open to progress if you want, if you know how React on the JS works, or just suggestion. And the app is available on this website. And there is this is the main repository. So this is the core. This is the electrodes of the desktop app. And you have equally a Docker to deploy it on your desktop on a server, as a server or directly on a server. And there is other private repository. This is mainly cluster. This is like Garnotel. This is like Azure. This is pay cluster. So there is a to-do list. First, the documentation, because there is some help for now in the software, but this is really limited. A big part is this one. Algorithm description and validation. It's quite important. This is validated, but clearly by hand for now. And editor improvement to be better to use on the slow interface and a lot of bugs. So thank you, and I let Houssam make you a demo. Je débranche. J'arrête de partager aussi maintenant.
Yes, hello, my name is Houssin. I will make some simulations with using Tanatloc, but the first simulation will be contact mechanics, and if we have time, the second one will be model analysis of a structure. So before doing the simulation, I will introduce very briefly the contact mechanics problem, and without going into details. So the contact mechanics is the Signoline's contact problem is the contact between a body and a rigid foundation or an obstacle. So we have a set of equations, which is linear elasticity equations, in addition to contact conditions, which will describe the non-penetration between the body and the foundation. So, for example, here, if we have a point X in its actual position, then and if y it's a projection on the rigid foundation, so X minus Y, scalar the normal vector, must be greater or equal 0, for example, in order to describe the non-penetration. The problem can be expressed as a constrained minimization problem. So the minimization of an energy, potential energy, over a set of non-penetration. Therefore, for example, here the set K will describe the non-penetration between the body and the foundation. So in our algorithm, the non-penetration will be described as will be a very simple non-penetration condition. For example, we impose for each node of the body to not penetrate the obstacle. So it's called node to segment discretization. It's very simple to make. And we have another contact formulation, more robust, but here we will present the simplest one. So yeah, it's a minimization of a potential energy with linear constraints, because we are in the linear elasticity case. If we are in the large deformation, we can make a fixed point algorithm. Yes, and we use the interior point method to solve our minimization problem, and more specifically IP out. So let's begin with the simulation. So the first one will be a contact between a body and a rigid block, and the second one, if we have a time, it will be a model analysis of a structure. So first, before running Tanatloc, we have to download what we call a Docker, and we have to run the Docker before using Tanatloc, and then after we can go to this website tanatloc.com, and we can choose we can download our Tanatloc if we have Mac OS or Linux. For my case, it's Mac OS, and then we can run Tanatloc. It has this shape. So if you want to make a simulation, for example, we can create. I have already a workspace, so we can create a new workspace. Let's call demo FreeFEM. Okay. Then we can create a new project. Let's, for example, contact FreeFEM. Okay. Then we have to drop geometries. So here the geometries must be, for example, for 3D geometries must be a step 5 or DXF file for 2D. How we can make a step file for 3D geometry? For example, we can use FreeCAD software, which is a open source and free software, and we can make our geometry and export it or save it as a step 5. For example, I will drop the first one, for example, the body. I don't know. So I can put our geometry. We must drop 2 geometries for the contact mechanics here. And the first one is the body, and then we'll add a new geometry also. We can simply drop our geometry, for example, here. Yes, and we can have our body on it. So to do simulate, you click on new simulation. For example, we have a different model here already done. So I will choose contact Murini not to segment. So we have a description of the algorithm here, and we can create on create. So about here we have a description of the algorithm, what we do, and then geometry. We can choose our size for the mesh. For example, let's say and then we can choose our material. For example, we will click on add material, and here for the body we choose this properties, and then we must choose this body, for example, and make add. Click on add, and then we will add another materials for the foundation, and foundation, and then we will pick a material, and in this case will be a foundation, that a rigid foundation. It means that have a rigid foundation, we will and then parameters. On parameters, we can add, for example, body force, and also we can choose our gravitational acceleration. So here in our case R0, and we can add boundary conditions. For example, here on this body, on this area, we will make an imposed displacement. So we click on displacement, and we choose our imposed displacement. For example, in the direction of Z, we will make -1, for example, and then we can name it so that and we click on add. And because we are in the case of contact mechanics, we have to tell tell Tanatloc where are the potential contact area. So I would call it contact 1 for the body, and there will be contact area. For example, we have to choose this space, then we click on add. Then also we have to choose the contact area for the rigid foundation, the potential contact area. Here in the Signorini's problem, it's not necessary to choose the potential contact area for the foundation. We will do it anyway. Foundation contact area, it will be avec le zoom. Ah oui, avec le zoom. Ah, ouais, ok.
Ça partage.
Il y a un peu de...
Un peu de jeu, non.
Ouais.
Ouais, ça, on t'a compris, parce que- Génial.
Non.
Frédéric, il y a un micro qui n'est pas coupé.
Albert maintenant.
Albert, désactiver le son. Voilà,
Ouais.
c'est fait.
So we have to select our resource to make a run. Select. And we can simply click on run, and then it will the simulation will start. So I don't know why on my computer it's very slow comparing to Simon. It's because the problem is the Mac. So here we can choose. We can yes, and I will stop the simulation and will show you, because we don't have enough time. So I will return, and I will show you. Yes, for a very refined contact. For example, I already done this for a finer mesh. So here we have the results. For example, we can see the mesh for the two, and we can, for example, the displacement on our body here, because we only have a body because the rigid the foundation is rigid, so we don't have any displacement. So we can show the deformation. So we'll click on this icon, and then we select, for example, wrap by vector. So we can choose our scale vector. For example, let's say 15, and then we will make run in order to show to see the deformation of the structure. Yes, it's very slow on my computer.
Possibly it's due to Docker.
Yes, Docker was also.
This is just a Python call, but the Docker has to start run the PV Python command on stop. I think this one is a long run.
Yes,
Yeah, this is very long.
very long. It's even very. Ouais, c'est plus long qu'hier, je sais plus. Ouais. So we can show the deformation. Ah non, c'est pas dans le bon sens. Pas dans le bon sens. And yes, and also parameter. We can also, for example, modify our boundary condition. So yes. Yes, for example, we can do another simulation. For example, model analysis. Its goal is to Allez, mettre sur le PC. Another. Sorry.
Plus Zoom, plus screen sharing.
Ah, tu as cliqué sur le rouge.
Ouais.
Si
That's
tu
the problem.
cliques sur le truc qui ferme la fenêtre.
The problem, yes. Okay, so. So yeah, I will choose model analysis. So yeah, we have here a ring. So the goal of the model analysis is to obtain the natural frequencies and the mode shape of the structure in order to see if we have the resonance phenomenon. And then here we have the ring. I choose the simulation model analysis. For example, we can see here it consists to solve a eigenvalue problem. So it's solved by RPAC, and then we can this problem can be transformed using a shift value sigma. It's in order to find the eigenvalues close to this sigma. For example, here by default sigma is equal to 0. So we have the geometry, the materials, parameters. In this case, parameters, we can choose sigma. Here by default is 0. We can choose another value, and we can choose how many mode shapes or eigenvectors we want. Here I already choose 18, and then here for the boundary conditions, we don't make any boundary conditions, so it's free. So also, it's in order to see the rigid modes. So it looks like this. So we can choose our mode number, for example, 0 or let's say 17. So we can choose the displacement. And here in this icon, we can see the eigen frequency. So here, because it's free, so from 0 to 5, we have 0 frequency. So it's the rigid motion. So it's the rigid modes, and thereafter we have frequencies. The frequencies for each mode. Frequencies with respect to mode shape. So let's say we want to show it looks like how it looks the shape mode 17. So we click on that, and then we select our filter or wrap by vector, and so scale factor equal 1. very slow on my computer.
Because this kind of stack is quite fast, so. And it's on ARM processor.
Yeah, this is an M1.
M1.
processor.
This is M1.
For example.
Possibly,
Yes, for
the
example.
code was for Intel and.
So
Yeah, Docker has a lot of programs to release on M1,
Yeah.
on M2.
so the mode shape 17, it looks like this. So the mode shape, it what the deformation will looks like when the structure is vibrating at the frequency at the corresponding natural frequency 17. Yeah, I will not show you the others, but for example, from the mode shape 0 to 5, we have a rigid motions. So that's all, and sorry for I don't think so. Okay, ouais, so thank you for
On a encore 5 minutes.
Oui.
On va juste montrer les moteurs.
ah, ok, tu vois.
Ouais. On va juste le tirer.
Ouais.
So this is just to show you what the editor looks like. So there is two parts. This is a beta version. There is two parts because when you write an algorithm, you have to specify the templates and the model. This is the description principally for the UI. So I will open the simplest problem. This is the Poisson equation. This is a really small code in FreeFEM, but here, this is 100 lines. So you can see some keywords, for example, there is some bar here. This is in 2D, in 3D, if you are in dimension 2 or 3. But there is some difficult part, for example, the boundary condition that come from, this is a JavaScript variable. Here this is all JavaScript. And here, this is FreeFEM, this is JavaScript, FreeFEM. So if you want to write things like this, you have to learn a little what is the template tool to write something. There is things that scale blocks to simplify the common parts, for example, the slash box, the FA space definition, the FA space function definition. There is some macros, but when you have to write the program, you have to write by hand the boundary recognition part. This is the harder one. After, there is equally some pre-written things for the server, for sensor, to save results. And the second part is just description. In fact, for example, to choose your finite element space, you just have to specify, you will use a select, and you have the choice between P1 or P2, for example. For the server, you can choose between generate months and UMF packer. This is months by default for all the script for now. And again, for the boundary condition, this one is object, for example, in linear elasticity, there is fixed displacement, surface force, and some default values for everything. So if you want to use it, you have to learn some things on EGS. This is the template engine. This one is just a JSON file. We will write a huge documentation for that. So, okay. This is just to show this one.